is well-known social choice theorist, and I am very creative to introduce the water. Water, please, your perspective.
Thank you so much. Thanks for having me here. It's a great. Thank you very much for having me here. It's a great pleasure to discuss some of our work here. So this is joint work with Susumu Kato, who is not here but maybe online, and Kohei Kamaga. And it's a contribution to population ethics. In particular, we wanted to look into possibilities of accommodating non-comparabilities. That is, we want to look at how can we, reasonably structured and general way find the methods of defining quasi-order rings that go beyond what is already being used. The standard example of quasi-order rings in population ethics is what is usually referred to as critical band utilitarianism, and our approach is a bit more general, and it is based on thresholds. It will turn out that critical band utilitarianism is a special case of what we do, and in the course of this presentation I'm going to provide this new class of quasi-order rings for variable population comparisons, and we look into a characterization and a few special cases. So if there's anything that you want to ask, any clarifying questions, feel free to interrupt me. Maybe not mid-sentence, but if there is anything, I have no problem accommodating questions as we go along. All right, so the basic setup, you're probably all familiar with it, is we have a wealth risk framework, so everything we do is based on people's levels of well-being in any two situations that we might want to compare. So our basic domain is what we call omega, and that's just the union of Euclidean n space for all possible population sizes. The object of interest is the quasi-ordering, that is a reflexive and transitive, not necessarily complete relation that allows us to rank these utility distributions, and of course these comparisons may have to work across different population sizes. So I use R to denote quasi-ordering on omega, and I use P and I for better, so it's a goodness, interpreted as a goodness relation. I use P and I to denote betterness and equal goodness, and because we only have quasi-orderings and not orderings, there will be some non-comparability and thrown into the mix as well. So as I mentioned in the short introduction, our approach is based on thresholds, in the sense that we want, rather than saying if we have a variable population comparison, which may often be very, very complex, we allow for the possibility of not committing ourselves and say we want to be reasonably safe in our judgment and saying, well, we only make a definite choice of one distribution being superior to another if we meet or surpass a certain threshold. So this gives rise to a class of threshold principles that we call threshold principles. I'm going to give you the general definition. Some of it may look somewhat unfamiliar and complex, but I will explain everything we're doing once I've written it down. All right, so basically we call these principles, or these quasi-ordering, threshold critical level utilitarian order, quasi-orderings. So threshold critical level utilitarianism operates by applying a threshold. So if you look at any two utility distributions, not necessarily of the same dimension, so pick any two population sizes, n and m. These are just positive integers. Take a distribution that involves n individuals, u, and the distribution v that involves m individuals. We use basically the critical level utilitarian criterion, and we try to extend it again to comparisons that do not necessarily to situations in which we do not have comparability of all possible distributions. So if we want to determine, according to such criterion, whether U is considered at least as good as V, we apply the critical level utilitarian criterion in the sense that we calculate the value for critical level utilitarianism of U. That's the gains of the individual utilities over a fixed critical level alpha. We subtract from that the corresponding critical level corrected value for V. But instead of just saying, okay, U is at least as good as V, if this difference is non-negative, we allow for a threshold, and we allow for two possibilities. One, that the threshold has to be met with at least inequality, or it has to be surpassed. This may seem like a little detail, but it is important when it comes to examining the properties of this class of quasi-orderings later on. So for that reason, I use a more general symbol, a little triangle that may depend on the difference in population size of these two distributions, the absolute value of n minus m, and you can think of this as standing for either at least as greater than or equal to or strict